Awesome. So I tend to like very conversational presentations. So those of you who've been to my presentations are aware. So I always like to start out by calibrating the audience really quickly. So, quickly, how many of you can raise your hand? Okay, most of you. That's a good start. Not everybody, that's normal. But more than 60% is a win. So real quick check also, how many of you are slightly jet lagged right now? Extremely jet lagged. Completely out of your globe. There we go. So this should be fun. I found over time that I get a lot of questions about presentations, basically that amount to, where do I find your slides? So, to make this simple, I've got the link right there on the slide, and I will pause briefly. There is a QR code. If you take a picture, you will get taken to the slide by the QR code. I discovered QR codes.
I discovered QR codes, and he's very proud of himself. He also figured out how to make puzzle pieces in PowerPoint, which you will see soon too.
Yes. So, we should probably talk about the title briefly. So, I'm going to be talking to you today about FIDO in a cloud-native world. And in some sense, what this is really doing is we're used to thinking of FIDO as the all-singing, all-dancing data plane of doom, which it is. But we'd like to provide some context about why this level of data plane performance, flexibility, etc., is actually really critical to the place we're all trying to get together in Cloud Native. And that's primarily what I'm going to be talking about here today. So it helps to start out by sort of asking yourself, what does it mean to be Cloud Native? There's a lot of varying opinions about this. It turns out there's not terribly good, crisp enunciation of it anywhere. Mark Fowler does probably the best job, as is true of almost everything that requires enunciation in software development world. But a good way to think about it is that microservices, by definition, are small and modular. They're little Lego blocks that you use to build up the things that you want in a system. They tend to be portable, meaning you can pick them up and drop them anywhere in the system. You can make multiple copies of them. You can move them around. That portability is not just in terms of hardware portability. It turns out that, although we do have that, it turns out that the ability to run them in a number of contexts within a system, often within a context like Kubernetes, but you have many systems that they're involved with. Obviously, you want them to be evolvable, and primarily evolvable in a way that allows you to apply CI/CD to them. This sort of portability, smallness, modularity means that you can roll out new versions, you can blue-green test them, you can roll out canaries. All these sorts of things are things that you typically do with microservices within a system. And then they tend to be very focused on outcomes, not on implementation details. So your microservices have ways that they interact together in the world. As long as they continue to meet the contracts between them, not just the APIs, but producing the necessary behavior, it doesn't actually matter what's happening within the implementation there. And then two things that are not necessarily intrinsically true of Cloud Native, but have come to be true, is being Cloud Native means running in Kubernetes. And being Cloud Native means running in a container. Right? Those don't intrinsically have to be so, but we've reached the point in history where that's basically true. Yes?
Question mark. If you look at the Kubernetes control plane, is it built out of microservices?
So you actually do find that it is predominantly built out of microservices. When you go and you look at, for example, the relationship between the kubelet that runs on every single node and the various things that it increasingly engages with over CRI, the container runtime interface, CSI, the container storage interface, and to a lesser degree CNI, the container network interface, which is sort of a little bit different than those. What you tend to find is a collection of microservices that collaborate together to provide that which you want in Kubernetes.
So you would not say that the way Kubernetes, the high-level architecture, in the sense of an API server that serves objects with desired and important state, and controllers that interact with those objects in their state, not through RPC, but primarily through objects in state, that is not microservices?
No, I found that to be entirely microservices. The contracts are clear. You've broken the problem up into small modular pieces. So no, I would say that is in fact a microservice, a good example of microservices.
But it's not the one you led with.
No, it's not it's not the one I led with. The point being that running in Kubernetes has become very much definitional for being microservices anymore.
I'm actually pushing on the definition of microservices. Many people think it's about RPCs.
No, I would agree with you that it's not intrinsically about RPCs. So, Kubernetes networking already focuses on outcomes. So, and it turns out the outcomes that it focuses on are really simple. Because it turns out that what developers actually care about are really simple things. So the first one is reachability and isolation. When a developer writes an application, fundamentally they care about being able to reach the other aspects of the system they need to reach over L3, right? IP connectivity, IP to IP. Isolation means that they may also care about being able to isolate components of their system, some of their microservices, some of their pods, so that only certain others can talk to them. And these two tend to go hand in hand. And then service discovery and service routing. So when you're building a collection of microservices that have to operate together in order to produce some task, and you're running a bunch of different replicas of those microservices, you need to be able to have them discover each other, and you need to be able to route whatever mechanism is being used through the system, whether it's RPCs or otherwise, to actually reach them. And this ends up being sort of the second thing that people tend to care about in terms of networking in Kubernetes. A few things you will notice that are not on here. So real quick show of hands. How many of you who work in Cloud Native, who work in Kubernetes, ever want to know this subnet exists again? Yeah, you're absolutely right. Why would you want to know that? Because these are the two things that you actually care about. So I'm going to real quick show of hands to see if we can skip past these slides. How are folks on Kubernetes basics? When you're dealing with deep networking people, sometimes it helps to talk through what is a pod, what is a node, what are labels, how do selectors work, that sort of stuff. Real quick show of hands, how many people feel extremely confident in those things in Kubernetes? Okay, so about half. So I'll do a really quick dash through, if that's fine with folks, just to make sure that we all come up to the level. So basic Kubernetes concepts. So in Kubernetes you have pods. A pod is one or more containers that share, for the purposes of our conversation, a networking context. And effectively this means that they end up with, they also end up running on the same node. Each of those pods gets a single interface with exactly one IP. And all containers in the pod share a local host. And all pods are subject to the network policy, can talk to all other pods at L3 in Kubernetes. Pods run on nodes. When you hear node, think server. Of course, you have multiple nodes, and you can label things. You can apply these key value pairs to pods so that you can actually subsequently come back and use those to make selections among the many possible pods in the system. So really quick overview on selectors. When you have all these things that are labeled, you can have a selector that says app equals foo, and you will pick out the two things that are labeled with the app label. You can have a selector that says stage equals prod, and you will pick out the two things that have the prod label on them. Stage equals prod label. Or you can build a more complicated selector and say stage equals prod, app equals foo, and you can pick out the thing that has those two labels in them. So very, very straightforward, but incredibly powerful. There's a lot to be said for powerful and simple at the same time. So reachability in Kubernetes, again, very simple and straightforward. The contracted Kubernetes is really, really easy. Every pod can talk to every other pod at L3. So Kubernetes does not have, need, or want the concept of an L2 segment, the concept of a subnet. IPs tend to only appear in places like statuses in pods, typically not in specs, although there are some exceptions to that. So this ends up giving you a very non-IP centric way of configuring the system. And then you get to isolation. Isolation in Kubernetes is via network policies. It's pretty easy. You have a pod selector, something that matches labels, that selects a set of pods that you wish to be isolated. And then you define things like ingress that also have selectors that define who should be able to talk to the isolated pods, who should be able to pierce that isolation. So again, very, very straightforward. Services in Kubernetes. This is how you do service discovery and routing. You define a service as a named thing. It has a selector. The selector matches it to a set of pods that provide that service. When you have pods arising and passing away quickly, and you don't have any a priori notion of how many replicas someone has decided to run of them, you have to have some way of identifying who provides a service that is independent of a simple enumeration of IPs. And so Kubernetes does this with labels and selectors. And then, of course, it also defines the ports that you expose from that service. And then this is also extremely nice for service discovery and routing. Service discovery typically happens via doing a DNS lookup, because every time you define a service, presuming you're running the DNS extensions, you get a DNS record that is created for your service that you can use to look up the VIP, the virtual IP number. And then when you attempt to open a TCP socket to that VIP, you will actually get routing through the system to a pod that provides that service. So the caller, taking an RPC example, never has to actually know the IP of the pod, just the IP of the VIP. And this also handles load balancing for you. So,
Yeah, I just wanted to point out there are headless services. A couple of KubeCons ago, Kelsey Hightower got up and said these non-headless ones are just training wheels, and you can take them off and use the endpoints.
you can, and it kind of depends on what you're trying to accomplish. But in the very simplest sense, this is the simplest case that most people start with. So, when you're looking at these things as microservices, one of the things that jumps out to you is we're doing all of our apps as microservices. We have a bunch of other things happening as microservices in terms of the controllers. It's microservices everywhere. Why don't we treat our networking as a microservice? And it turns out this is actually quite easy to do if you have the right building blocks. Because Kubernetes is, again, already focused on outcomes. So that part, the hard part, is done. But the things that most network providers for Kubernetes don't give you is sort of the portability runs anywhere. The fact that you can put it all in a container, you can pick it up, and you can move it. Because much of networking today, even for Kubernetes, as an implementation matter, is still being done in the Linux kernel. Which means you're dependent on what is or is not present in the kernel. Which means as new features come out, as improved ways of doing things come out, you have to wholesale upgrade the node all the way down to the kernel in order to take advantage of them. So we'd like to see that improved. Evolvability, again, if you're stuck with your networking dependent on kernel features, then it's difficult to evolve because a kernel upgrade is a very serious affair, and the cycle time on a kernel is very long. The time between someone trying to write a patch to do something and it coming out on the other end in distributions can run 2 to 3 years, which makes it very difficult to do rapid iterations in networking. And then, of course, CI/CD, I'm sure there are people who use CI/CD to roll out new server images, but it's a really ambitious thing to try and do fast scale on that sort of behavior, just because the amount of disruption involved in revving a server engine tends to be very large. So this is where FIDO comes in, because with FIDO, we have this incredible data plane that is extremely performant, that's extremely efficient, and that's pure user space. And the fact that it's pure user space means that you can roll it up into a container and you can do all the things with it that you normally do with containers in terms of evolvability, portability, CI/CD, all the rest of it. So there is one implementation currently that does this called Conti VPP. It literally simply rolls up into a container the VPP data plane, which is pure user space, and an agent that allows it to, that configures that data plane. Because what you really want out of this situation is precisely what the Kubernetes API promises you. So you need some kind of an agent that can listen to etcd and the API masters, figure out what it is it's supposed to be doing, and program the low-level details of the API, or of the data plane. Any questions so far? Okay. So this is portable, because again, you're containerized purely in user space. It runs anywhere. You don't need magic kernels here. If you discover that you want to improve the performance of a particular implementation, or even change entirely the way a particular thing is implemented in terms of the networking features you're using on the wire, you don't have to wait for kernel revs to get there. Sorry, what? No, you don't need special NICs. You can use DPDK drivers, which can be used against, you can get either DPDK drivers that are very specific to NICs and get extremely good performance, or there are DPDK drivers that are more generic that will tend to work on most NICs. So you don't need magic NICs for this, because DPDK is handling the driver layer for us. And then binaries, we currently publish binaries for VPP for both x86 and also, as Brian will talk about later, for ARM. We're actually very pleased to be publishing now ARM binaries in the form of Debian and RPM packages. So this is, of course, evolvable, which means you can bring CI/CD into it. Because now if you're talking about rolling out new networking, it is simply the upgrading of a container in the system. And this can be done in a fairly straightforward way, and you can do it in a way that's fairly quick and recoverable. So yes, there will be a tiny blip, but nothing even approaching the blip that you get for a reboot of the device, much less the upgrade of a kernel. So really quick walkthrough of the Kubernetes Microservice API Architecture for KubeCon. At the heart of it, as you have for most things in Kubernetes, you have the Kubernetes, went too far. You have the Kubernetes master. This is the API server. All the things where you're defining your pods, defining your network services, defining your Kubernetes network policies. The normal sorts of things happen flowing down through kubelet, including flowing down through CNI, to the VPP agent, which handles the provisioning of the data plane. Additionally, that VPP agent, in order to provide things like network policy and services, which lifecycle independently from pods, is also listening directly to the API server in Kubernetes. So that if you deploy a pod and then you deploy a network policy that applies to it, that network policy gets applied to your already running pod. The VPP data plane itself is linked up to whatever your external network is. This gets to your point about drivers. We have DPDK drivers. We have a number of different ways of going about this. The ODP guys have written some drivers of their own as well. This links you out to simply whatever your network is, be it v4, v6. You can do things like segment routing with it, whatever makes sense. And then connecting to the pods, you can either use vETH, as most people do, or we actually have some ultra-efficient options coming online now with TAP v2 that outperform these. Because the kernel introduces a fair amount of overhead into the system. The more work you leave to the kernel, the slower the linkage tends to be. Any questions? Yes? No, Mike, you're great. I like questions.
Yeah, so earlier you were talking about how this is, I thought you were going to say, this is software inside each pod.
No. I mean, when you get to later in the day, and there are some people who will be talking about cloud native NFV and various approaches to it, in those circumstances, you might want to deploy a VPP data plane in each pod. It turns out that there are pros and cons there. And so typically speaking, you are going to want one vSwitch pod. And the reason is actually really fundamental, which is somebody has to own the hardware NIC that goes out of the box.
Well, I thought that's what virtual functions were for. Well, I mean, okay, someone has to hand out the virtual functions.
Well, it all depends actually on what you're doing. It turns out that SRIOV, pure matter of opinion here, SRIOV was a huge deal when you were dealing with VMs, because all that goes in and goes out to a VM are terrible. It's incredibly slow. And so slicing up your actual interface into things that look and behave like physical interfaces was a huge advantage. But they were sort of finite in number, and you had to do a fair amount of work there. As a matter of my personal opinion, while I believe there will still be use cases where SRIOV will make sense, I believe you will see a large number of use cases where it actually makes no sense at all. Right? I'll give you a really classic example. So, say I have two, apologies, it's going to be a cloud native example. Say I've got two different CNFs, Cloud Native Network Functions, sitting on the same box. I don't want to use SRIOV up and down between them, because then I've got to bump down to the PCI bus. And the PCI resources are extraordinarily limited compared to the memory bus, right? So it makes no sense at all to be plugging SRIOVs into these things if there's going to be any intra-box chaining at all, right? And it turns out that increasingly as you sort of roll through things, while again, there are small use cases, I think the use cases for SRIOV decline tremendously in the cloud native world.
All right. I guess another surprise, I thought we were all about cutting out the kernel, but if we're talking about VETHs and TAPs, we're not cutting out the kernel.
Well, so it turns out, here's the trick, and you'll hear a little bit more about this later today. Most applications do need a TCP host stack, right? So if I've got an application that's just going to eat IP packets or Ethernet frames, then I have other methods, and you'll hear some of those from Damian about MemIF, that are awesome. But if I need a TCP host stack, then you need something to provide that. Currently, and you'll hear a talk later today from Florin, there's work going on at a TCP host stack that is pure user space in VPP. I believe you'll also be hearing a talk from Ching about DMM, which is building the blocks to do an LD preload shim that will allow normal applications without recompile to be able to take advantage of it. These are things that are coming up today. They're in progress. So as time moves on, more and more of the kernel gets chipped away. But in the immediate now, someone still has to provide a TCP IP stack, something that meets the Berkeley socket API to your existing applications. And right now, the ways that actually do that 100% are using VETH or TAP v2. And there will always be some applications that have statically compiled themselves where you're going to have no other option because they're making syscalls, right? There's nothing to shim. Did that answer your question?
Yes, thank you.
Excellent. And you were a great straight man. You gave me the opportunity to introduce like 3 speakers in one shot. So, goals. So there are all kinds of really cool things you can do when you make networking a microservice in terms of the upgradability, in terms of interesting things you can do with the implementation, in terms of new features that can be introduced over time, in terms of cloud NFV. So I'm going to give you one simple use case that is absolutely imperative for absolutely everyone, and that's density. Because density is a dollars and cents issue. Right? So the number of pods that you can run on a single server, particularly as the world is shifting towards bare metal Kubernetes, and our friends at Intel insist on pushing more and more cores into every box, what you find is that you want to run more and more workloads. As you run an increasing number of pods on the same box, the overhead involved in the networking between them with all of the policies and all of the services and all the things that are scaling up gets to be very large. The kernel was never designed for networking at that scale. VPP was. And so it does it enormously more efficiently. And so you can then, the goal is to be able to roll out more workload density on the same node by virtue of wasting fewer cycles in an inefficient implementation of the complexities of networking that come from breaking the world into small pieces like this. And so this is a headline, straight dollars and cents CapEx case that is why this is actually important to everyone. Even if you don't think you want anything new or different from what you're getting today from Kubernetes, I guarantee you that you want to spend less dollars on servers. Any questions? Cool. So today's talks, and you were a great straight man for this, Mike, much appreciated, are basically the pieces of this puzzle. So first you'll hear a set of talks about open benchmarking. It turns out when you actually want to make these arguments for real around density, around performance, around everything else, you need to have reliable, reproducible benchmarks that are being run in the open and that can be reproduced by anyone. And so we'll have some talk about that. As you pointed out, if you want to continue to chip the kernel out of your way, you've got to have user space host stacks. And as you move to user space host stacks, you discover that you have all kinds of interesting options, including bringing in new L4 protocols, which I think Marco will talk about a little bit as well, Marco Verlies. Additionally, you need to have some way to shim the legacy applications, which is Ching's talk on DMM, so that you can have unaltered applications take advantage of these new efficiencies. Then we'll have a few talks that talk about Kubernetes and Envoy integration and ways to sort of speed that up. There'll be some conversations about broadening of the hardware support in the system. I know that there's a great deal of ambition from the ARM guys to go edge to core. And so for that, you actually want to make sure that all these components performing very well from the very bottom of the metal up are performing. And Brian will be talking about that. Then we'll have several talks about Cloud Native NFV. These are the building block pieces of how if you're one of the people, and there are probably $100 billion a year in CapEx worth of people who have this problem, who are trying to move their NFV solutions into the cloud native world, the kinds of things that have to be solved and the kinds of solutions that are already emerging to solve them. And then finally, at the end of the day, what makes this all work and makes this all grow is an expanding ecosystem. And so we'll have talks and conversations about that expanding ecosystem. And I believe that's my last slide. So, yeah. So putting back up the how do you find this talk slide, because I was very excited this weekend about QR codes. So, questions before I close? I can always count on you, Mike.
All right, I'm just going to leave this thing here for. You go.
Is there going to be like a schedule page we can refer to with all the slides pointers on it?
That is the goal. I have been let down by that goal before in other conferences, and that's why I put the QR codes on the slides.
Yeah. Yeah, and I'll talk to the events team. It does require all of our presenters to get their slides to the events
and
team.
I may have been one of the people who doesn't do that reliably in the past as well.
Yeah, so that might be perhaps why that has let you down, Ed.
Sometimes it's me, but sometimes it's not.
Yeah, but I'll go find out if they're planning to upload the slides. Cool. I can go check on that during break.
Does anyone else have questions? Yes. It is a CNI plugin, yes, but it's more than that because CNI is actually a very, very simplistic SPI. And so if all you have is a CNI plugin and you're not also listening for what's happening with services and network policies, you're going to radically fail to provide the Kubernetes networking API that people expect. So yes, it's a CNI plugin, plus the other pieces necessary to actually do what Kubernetes wants. Awesome. Other questions? Yes?
Just interested in your perspective. What's going to win in the multi-network interface for containers? Is it going to be Multus or is it going to be the Legato approach?
So first of all, I am not the person to ask for a totally objective opinion on this. Just saying. So here's the thing that I observe about this entire conversation, which is that there were a bunch of places in Cloud 1.0 where we took physical infrastructure, we took all the physical objects in our world, and we slapped a V in front of them. So machines became virtual machines, interfaces became V interfaces, V subnets, V load balancers, V firewalls. And it turns out this is, generally speaking, a terribly unpleasant idea. Because most of those physical things exist because they had to, and it's their collection that gives you the thing that you actually want. And so approaches, when you look at what Kubernetes has done, talking about reachability and isolation, and talking about service discovery and service routing, you will notice that nowhere do you have the slap a V in front of an approach. There are no V interfaces, there are no V subnets, there's none of that. So I think we have to find a way forward that is more cloud native in its approach for those sorts of problems. And Legato is an excellent start on that. There's other work going on inside the Legato community for network service mesh, which is another fun thing that's coming up that I think is actually providing a really nice framework that lines up well with what's happening everywhere else. So I think those approaches are actually the ones likely to bear fruit. But again, I'm intensely biased in this area, so please be aware of that. Other questions? Yes? Yep.
Okay, well, in Kubernetes, especially for the resource quality, the main two resources that are currently are very good. There is very good isolation for is the network, the memory, and the CPU. Mm-hmm. However, for the network, there is none. So, for example, if you on one node you have a pod which is very network intensive, it can starve all the other resources. So, what your thoughts on that? And
yeah, so I think there are two kinds of problems that happen there, right? So one problem is relatively solvable in a way that's very familiar to how things have happened otherwise in Kubernetes, which is if I've got a certain amount of resource in terms of bandwidth coming in and out of the box, then we've got a really nice framework with the device plugin API in Kubernetes, which is an extension of how resources are handled for CPUs and memory, that will allow you to allocate some finite hardware resource that lives on the box. So I would expect that kind of a problem to be solved in that kind of a way, right? Yes?
But if it's only that, right, you don't even need device plugin, right? I mean, in the same way, the CPU and memory are not individually allocated by the scheduler, but en masse, right? The scheduler is extended, already extensible, right? You can already tell the scheduler, hey, this node has so much bandwidth in and out of the box, this pod needs so much bandwidth in and out of the box, the scheduler will add those up, respect the capacity constraint, and store it.
I was
Right,
talking
but you
about
need to be able to enforce it because somebody can misbehave, right? So there's a little bit more involved there. But so I would expect them to be handled that way. There's a second harder problem, which is basically dealing with the end-to-end networking issue around being able to get bandwidth between things. And since that involves the physical network, it's a much more complicated problem, especially since the number of things and places that can go wrong, even transiently, is very large. That I expect to be a much harder, more interesting, and more complex problem to deal with. You had a further comment or question?
no, thank you.
Okay, cool.
Any other questions?
Of course you can, Mike.
So it's not just an implementation.
It also begs a serious API question. In Kubernetes API, there's no place where you get to say, I need this much bandwidth between here and there, right? So it really needs API innovation as well as implementation things.
Yeah, absolutely. I mean, you could imagine a world where you cobble that into network policies in Kubernetes, but cobbling has a poor history in general. So you very well may want to think a little bit more about that. But I think the style of what happens there, which is we will select some set of things here and some other set of things there and some relationship between them, that pattern I expect to apply to the end-to-end bandwidth problem. But again, that's a much harder problem to actually deliver implementation-wise. Any other questions? Awesome. You guys have been a fantastic audience. Thank you so
Great.
much.
Thanks, Ed.